Okay, so um, at instant one, we can still use all the information we had last time. So gravitational potential energy is 7.84. The spring potential energy is 0.32. Kinetic energy is 0. And now at the bottom, we don't know what H is, but we know that the gravitational potential energy is going to be 98.1 H. Please stop me if you don't follow something. Um, the spring potential energy is 1/2 times 100 times H squared. So I'll just write that as 50H squared. And what's the kinetic energy? Yep. So conservation of energy says 7.84 plus 0.32 is equal to 98.1 H plus 50 H squared. And you can write that as 50 H squared plus 98.1 H minus, what's this? 8 point is equal to 0. And what do you get for H? Negative 2.8404. And yeah, what do you get for and the other one then is the positive 0.08. So this thing is just going to keep oscillating between those 2 points. The point up here it was released from, and this point way down low, 2.04 meters below the resting length.
You're making the assumption that in the problem that 0.08 is the top of its spring, although 0.05 is not
Right,
the bottom of its spring.
right,
And even though it's not said that that's it, you're not just holding it up halfway and then letting it go and it going back.
right. That's right. So we just for some reason chose to figure out what the speed was just as it passed through 0.05.
So you chose instant one because it has zero kinetic energy.
Yeah, it's a no stuff want stuff thing.
Sure.
So we knew no kinetic energy there, and we knew the heights. So we knew a lot of stuff there.
Okay.
Any other questions about that? Yeah. Yeah, you'd get a different answer, but yeah, right. So you just choose whatever point you know heights and speeds and stuff like that.
So that's just the bottom point when it's compressed. That's just the lowest it will go when it's
So it's like this. So the spring's resting length is here. It's lifted up 8 centimeters. And released, and it goes all the way down to 2 meters before it starts to come back up. And it'll come back up and get exactly up to where it started before and just keep repeating that cycle. That's very asymmetric with respect to that resting length. It's because that spring was so weak. If the spring was stiffer, if K was 1,000 or 10,000, then this asymmetry would be less because the effect of gravity would be small compared to the effect of the spring. So if the spring stiffness was 1,000,000,000, it would basically go from 0.08 to negative 0.08, and it would go really, really fast between. A pogo stick? Well, here's one thing that's a little like unsatisfying about spring constants. The length affects it. So the same spring, if it's twice as long, has, I guess it has twice as big a spring, half as big a spring constant if it's twice as long. The shorter it is, the bigger the spring constant is.
So you're randomly assigning a spring constant?
I did when I gave the problem, but it's something you can measure. A pogo stick spring, say it's this big and strong enough to not bottom out for a 11-year-old kid or something. I bet a couple thousand. The little springs that we have in the lab, I guess we haven't done any labs with springs, but they're more like 100. Any other questions? Okay, let's do one more calculation related to this. So this is kind of interesting. Like, have you ever thought, like, at what year do you think technology had advanced to the point that there was high-speed video fast enough to measure a bullet's speed? You know?
What year?
Yeah.
1928?
Yeah, that's what I'm talking about. Yeah, right. Yeah, right.
Before the people doing stuff?
Yeah.
Go down?
Yeah. I mean, I don't know. I would guess later than that, but I don't know.
No, I wouldn't.
You wouldn't?
Or color, yeah. Lots of old black and white ones in the museum.
But could get 2 pictures of a bullet shot out of a gun. You know, that's the,
Not nearly as many frames per second.
yeah, with not, so I would think you would need a lot of frames. Oh yeah, that's a good way to answer this question. Yeah, I mean, I would guess I don't know the answer, but I would guess but anyways, even if it's 1928, like,
I think when the early movies started, you just take 2 frames of the movie. You know?
yeah, right, but if those frames aren't, yeah. Like you have to be close enough that you can see the bullet, and then you only have this much range, and so, you know, it has to go pretty quickly to be able to get 2 frames where you see the bullet. Okay, well, I'm going somewhere with this. Yeah. Okay. So yeah. So let's say that it's recent, because that makes my story more interesting. Do you think before that nobody knew how fast bullets went? Like, that doesn't seem right, does it? Is it? Like, so how do you measure the speed of a bullet? You could do that, but it's like an average, you're right, and there's a ton of friction going on, you know?
The same way we were measuring when the cars were going through that laser.
Yeah, so you could do stuff like that, but I'm just thinking, like, having the technology to do that kind of thing, like, that's a lot of technology. Like, what about when, in the old days, like, did people have no idea how fast a bullet went? Like,
Probably. They didn't care. Got the job done.
yeah, right. But they have to know if it's going to get the job done.
Or when.
Because if you shoot an animal and don't kill it, it's going to be mad. So, okay, here's what they did. There's a way to calculate this with no technology, and it's pretty cool. It uses conservation of linear momentum and conservation of energy.
So you need the whole thing.
What?
So you knew the whole time.
Yes.
Possible.
Yes.
So you wanted us.
Yeah, I didn't just bring it up because I thought it would be interesting to talk about. So what you do is, you know, the mass of the bullet is relatively small, but it's going really fast. The numbers I chose, I know they're wrong, but I chose an unbelievably massive bullet. I chose 50 grams. I don't know why I chose that. That makes no sense at all, but that's what I have in my notes, so that's what I'm going to use. But the point is, it's small, okay? Like, and it's going really fast. And the speed, I chose 1,200 meters per second. I think that's closer to the ballpark. And I don't know. Are there keys right over there? I'll look for them. Yeah, see ya. So what you do is you shoot this relatively light, relatively fast bullet into a heavy mass. So let's say this is 15 kilograms, made out of wood, a big chunk of wood. The bullet lodges in the wood, and then the whole system swings up. But once the bullet lodges in the wood, that heavy mass isn't going 1,200 meters per second anymore. It's going something that you can actually, slow enough that you can actually follow its motion with your eyes. And so now you can see how high it swings up, measure its highest point, and back calculate what the speed of the bullet was.
People actually did it?
Yeah. And actually, I don't know. I mean, if you think about the expense of, this is an accurate way to do it. When you think about how expensive it would be to use lasers or high-speed video or whatever, I bet this is still used, you know, somewhat, but I don't know, maybe not. Maybe people just look on their gun manual and it tells them how fast.
Well, I mean, the gun companies probably started it.
Yeah, right.
Research and development.
Right.
You know.
So we're going to do it a little bit, like not exactly the way that you do this calculation. I'm going to do it in a way that the math is a little simpler, but you'll sort of see how this all goes together. Okay, so instead of giving a height and back calculating the speed, I'm giving a speed and we're going to calculate the height that this swings. Okay. And to do this, this is called a ballistic pendulum, by the way. You break this motion, this whole set of events, into two separate parts. The first part is just the collision. And if the bullet sticks in there, is it an elastic or an inelastic collision? Inelastic. And then after the collision, the bullet mass combination just swings from here up to the highest point, and we'll use conservation of energy for that. Okay, so first the collision. What we want to figure out is, once that collision is done, how fast is that combination of the mass and the bullet moving? Like right after that bullet lodges in there. So we'll think of a top view. There's the bullet. The top view really looks just the same as the side view, but and if the coordinate system is oriented this way, then conservation of linear momentum, inelastic, says 0.05. That I've like probably elephant gun bullets aren't 50 grams, right? How much, you have any idea how much a bullet weighs?
I don't know about grams, I just know greens.
Oh, I don't know that, how that converts.
I wouldn't doubt some high power rifles are that heavy.
Really?
I know nothing about guns though, so. What? I don't know. Have you seen how big they are? They are heavy. Yeah, but the big thing isn't the bullet. Oh, I'm aware of that. Okay. Let's just say my knowledge comes from Call of Duty, so it's pretty basic.
Yeah. Okay, so this is the momentum of the bullet before the collision. Before the collision, the mass is just hanging there, so that has no momentum. And after the collision, they travel as a single thing after the collision, so we can think of it as just a mass of 15.05 kilograms times the velocity vector. And so you get Vy is equal to 0. Vx is equal to what's, so what, 60 divided by 15.05? What is it? 91? 99. And now we're going to do the swinging part. If you think of the forces acting on the ball, there's the weight, and there's a tension force, and it's swinging in a circular arc. So that tension force, even though it's a non-conservative force, is a centripetal force during a circular motion, so it does no work.
I have an answer. It says the 50 caliber bullet weighs 46 grams.
Wow.
For 700 play on grades.
How much does a deer hunting bullet? Oh, yeah. Okay. So instant 1 is going to be that instant right after the collision. Instant 2 is going to be when it gets up to the highest point. The only conservative force is gravity. So the gravitational potential energy, well, we have to choose our zero height. What do you want to choose as the zero height? The top?
Zero velocity.
That's an unusual choice, but let's do it. Because you can do it anywhere. So usually people choose the bottom, but let's choose the top. Yes, okay. We can. Okay, so.
At instant 1, the tension is pointing straight up, right?
Right.
So that's a, you got a diagram now. Second instant.
Yeah, that's just sort of at a general moment in the path. So we have 15 times 9.81 times 0, so 0 potential energy. And the kinetic energy, oh, I said 15, but it's not 15. The whole thing is swinging together, so that should be 15.05. You still get 0 there, but that's important for understanding how this works. The kinetic energy is 1/2 times 15.05 times 3.99 squared. Can someone calculate that? 15.92. And then at instant 2, the potential energy due to gravity is 15.05 times 9.81 times the height that we're trying to calculate. What's 15.05 times 9.81? Oh. Thank you. What is it? 119.8. Okay, great, thanks. And then what's the kinetic energy at the highest? That was what we just calculated from the collision. So that's the speed of those two right after the collision ends. So at the highest point, before it turns around, changes directions, the speed is 0. So 0 kinetic energy. So conservation of energy says 0 plus 119.8 is equal to 147.64 H. So what do you get for H? So 0.81 meters. So you take this this bullet that's moving really, really fast, and which you have no chance of being able to measure anything by sight, and you turned it into a slower motion that makes this thing swing up less than a meter, measure where it is, and it's kind of cool. No, it doesn't. As long as it's long enough. You know, it doesn't work if the rope is so short that it just does this. But as long as it's long enough, it'd be the same no matter how long the rope is. Although, no matter what material you had, the longer the rope is, the more it's going to stretch. And stretching messes up this calculation. So you wouldn't want it much longer than it had to be. Yeah, but even a wire would stretch, you know. I mean, and the longer it is, the more it'll stretch. So, but yeah, I mean, I think so. If you used a 1 meter long wire or something, you'd get good results with that. Okay, any questions about that? All right, that's it.